Okay, so in our next video for chapter 4, this will be our second video in chapter 4. We're going to talk about the multiplication rule, and it says the probability of A and the probability of A and B is equal to the probability of event A occurs on the first trial and event B occurs on the second trial. So these are n probabilities. For these problems, you want to remember that you are multiplying. Oh, you know what? Let me do that in this color. So you're going to be multiplying for these problems, okay? So notice here, there is a chance that you have overlap once again, that the probability of the first event affects the outcome of the probability of the next event. Think about it this way. Let's say you had a bag of 10 marbles and 7 of the marbles were red and 3 of the marbles were yellow, okay? So if you pulled out a marble, that means that now there's only 9 marbles. So you could say you had 7 red and 3 yellow, right? So if you're going to draw 2 marbles, when you draw, so I could say the probability, oops, let me write this better. Probability that you draw red and let's do probability that you draw yellow. I want to do that better. Probability of a yellow and another yellow. So that means that you're going to draw yellow on the first one, and then you're going to draw yellow on the second one. So the first thing I want to talk to you guys about is what's the probability of drawing a yellow, right? So if we just talk about the probability of drawing a yellow, well, there are 3 yellows out of 10 marbles. So this would be 3 out of 10, okay? Now, what's the probability of drawing a yellow knowing that you already drew a yellow? Let me change the font on this pen, sorry. Or not the font, but yeah. Okay, so now this is a fancy way of writing, and we're going to learn a much faster way to write this later on. But I just want to kind of talk to you guys about this. Now, if you have 1 marble in your hand that you already drew and it was yellow, how many are left? Well, that means that there are 2 yellow marbles left, right? But how many total marbles are left? There's only 9, right? Because we took 1 out and we set it on the table, we still have 1 left. So this is something that we're going to be working with. This is called independent versus dependent, okay? So the first draw definitely affects the outcome of the next draw, okay? However, what if I were to tell you that you reach in and you pull a marble out, what's the chance you get a yellow, and then you put the marble back in, you don't keep it, you put the marble back in. The next draw would still be 3 out of 10 to get a yellow, right? Because the first draw you put back. So that's something that's called independent, okay? So the first draw does not affect the next, or the first event does not affect the next event. Dependent means that it does affect the next event. Okay, so it says, when event A having already occurred affects the probability of event B occurring, we say that the events are dependent, since the likelihood of event B happening depends on event A happening. So here's just one to just kind of talk about. It says, let event A be graduating from college and let event B being owning a home. So do you think the occurrence of event A affects the probability of event B, and why? So yeah, you guys, I'm not going to write this out, but you guys could just kind of think about this and write down why you think. But do you think if you have a college degree, that would affect whether you're going to be able to buy a home or not? I would hope so. I mean, I think a lot of us go to school to try to get a better job, to have, obviously we want to learn, but a lot of us go to school to get a better job and, do something we enjoy. And a lot of people that, get a degree, they have a better chance of getting a home. So getting a degree definitely affects the outcome of, or affects buying a home, okay, or owning a home. Okay, so you guys can write out your explanation of that. It says, when event A having already occurred does not affect the probability of event B occurring, then we say that the events are, hold on one second, I'm sorry. Sorry about that, I had a little technical difficulty. So when event A having already occurred does not affect the probability of event B occurring, we say that the events are independent, since the likelihood of event B occurring or happening in no way depends on event A happening. Say you toss the same coin twice, okay, one side is heads, one side is tails, and it's fair. So it says, are these events dependent or independent? So if I toss the coin the first time and I get heads, that was a 50-50, right? I had a 1 out of 2 chance to get heads, right? And now when I flip it again, what's my chance of getting heads again? It's still 1 out of 2, right? It's still 50% or 0.5. So the thing is one flip to the next flip did not affect the outcome of flip A to flip B. So this is something you guys have to think about when you're dealing with problems. Am I dealing with an independent event, or am I dealing with a dependent event? This is obviously an independent event because the first toss does not, or flip of the coin does not affect the outcome of the next toss of the coin. Okay. So if A having already occurred does not affect the probability of event B occurring, they're independent, then the probability, so this notation right here, this little symbol, do you guys see this symbol right here? That means given. Okay. So it says the probability of B given A is equal to the probability of B. What that is saying is the probability of B occurring, given that you already know A occurred, is just probability B, meaning that A does not affect B, because who cares if it already happened? It doesn't affect B because they're independent events, since B does not depend on A. In other words, knowing that A already occurred has no effect on the probability of B. Note, the probability of A given B is equal to probability of A is also true if A and B are independent, okay? So here's the big one. Here's for independent. This is the nice, easy one, okay? This is our nice, clean one for independent events. So it says, say that you toss the same coin and a 6-sided die at the same time. So it says, what is the probability the coin lands on tails and the die lands on a 4? So we're going to say probability that we land on tails. So I'm just going to use T for tails and a 4. Okay, so and I'm just going to use my formula right here. Probability of event A, probability of tails, times probability of getting a 4. Okay, because the probability of getting a tails is 1 out of 2 because it's a fair coin. And then the probability of getting a 4, well, how many sides are there? It's a 6-sided die, and there's only a 1 4 on there. So this is going to be times 1 out of, not 1 out of 4. There are 6 sides, so there's 1 4, so 1 out of 6. So this would be 1/12. And that would be our probability of flipping a tails and rolling a 4 at the same time. There's 1 in a 12. Okay. Says, what is the probability a coin lands on heads and the die lands on an odd number? So let's do probability of heads and odd. So while we know that the probability of heads, I'm going to write probability of heads because these are independent events. Remember, the coin flip doesn't affect the die roll, times the probability of odd. Well, we know this is 1 out of 2. Now, how many odds are there on a 6-sided dice? Well, there's 1, 3, 5, and that's it. So there are 3 odds out of 6 total possibilities, right? So 3 of the 6 sides on a dice, you got a die, right? And it has 6 sides, and it's 1, 2, 3, 4, 5, 6. And how many of these are odd? 1, 2, 3. So that's where I got my 3 from. How many total are there? 1, 2, 3, 4, 5, 6. So that's where I got my denominator. So now we end up with, well, 3 out of 6 is 1/2. So we're going to get 1/4, right? Because 1/2, that would be what? 3/12. 3/12 is the same as 1/4. So the probability of that happening is 1/4. Okay. So hopefully you guys are doing okay so far. Again, if you guys have any trouble with this, make sure to show up to class and talk to me about it. So it says the American Red Cross says that about 45% of the US population has type O blood. 40% have type A, 11% have type B, and 4% have type AB. Among 2 potential donors, what is the probability that both have type O? So remember, what I'm going to do is I'm going to go into a crowd and I'm going to grab somebody out of the crowd, and then I'm going to grab another person out of the crowd. What's the probability that both of these people that I drew have type O? So probability of type O on the first draw and type O on the second. Now, here's the thing. They don't tell, this is the US population. So there's something you have to kind of consider. Technically, if you reach into a crowd of 10 people and you take one of them out, is there less people than you started with? Yes, and it kind of changes the probability of the next event. So this should be dependent, but we are going to treat it this as independent. Why? Because it's the entire US population. Okay, so now think about this. If you take one person out of the entire US population, is that going to affect the outcome of the next draw? Well, technically, yes, because there's one less person. However, the numbers are so massive. You know, the US has 350 million people, right? So if you have 350 million people and you take one out, you're not even going to notice the change in probability like until like the 20th decimal place or something, you know, something ridiculous. You won't even notice it. So we're going to pretend anything that doesn't really have, or that has such a large population that taking one from it doesn't affect it, even though it would be dependent technically, we treat it independent. So we're going to treat this as independent, okay? So this is going to be the probability of O times the probability of O, okay? So the probability says that US population has type O is 45. So I'm going to do 0.45 times 0.45. Okay, let me see what we get on our calculator. I get 0.203 about. So this is approximately I believe it's 0.203. So if we want percentages, then we would say 20.3%, only because, you know, they were using percents in the beginning, but 0.203 would be good. Okay, let's look at the next one. So this would be our correct answer. The first type A and the second type has B. So probability of A and B. So this would be the probability of type A times the probability. And remember, I'm using independent because it's such a large population that for ease of working with this, we're going to treat it as independent. So we don't have to subtract 1 from 350 million. Okay. And then this would become probability of type A, they said, is 40%. And then probability of type B is 11%. So I think we should be good on that. So let's see what we get here. We get 0.044. Let me just double check this again on my calculator. 0.4 times 0.11, we get 0.044. Okay, so that's not approximately, that is exactly 0.044. So this is 4.40%. Okay, but that's the probability. But if you wanted to convert it to a percent, you could. Okay, so then it says at least one has type A. Okay, so now we're going to get to something a little different. Now we have to be careful because it says at least one has type A. So that could be probability of at least one type A. So what does at least one mean? Well, that could be, you know, and I'm going to skip the writing the probability of A. Probably, I'm just going to write for a second. What are the outcomes, right? So this could be at least one means that if I have two people that I'm drawing, the first draw has type A, or the second draw has type A, or they both have type A, right? That's what it would be, okay? So that means we have to add all these probabilities up, okay? So we're going to say that we could have this scenario. Remember A and A complement, okay? Plus, we're going to have to add up A complement and A, right? So this means that the first person was type A and the second person wasn't. That could happen, right? That's a possibility. Or there's another scenario where the first person wasn't type A, but the next person was. But there's another scenario that we would count that they're both type A. Would that still be at least one type A? Yeah, the first person was type A and the second person was type A. So I could do all of those situations. So that's going to be, let's see here, type A and A complement. So we know that type A is 40%. So I'm going to do 0.4 times, let's see here, 0.4 times 0.6, right? Because A complement, if getting type A is 40%, then the complement of that would be 60%, plus 0.6 times 0.4, plus 0.4 times 0.4, right? Probability of getting A and then the next person also A. So now when we multiply all this out and add all this up, we should get 0.64, but I'm going to double check this real quick. So 0.46. So let's do 0.4 times 0.6 equals, now I'm going to double that because there's the other one's the same, plus 0.4 times 0.4. Yep, 0.64, so we're good. Okay, now there's an alternate way we could have done that. We could use the complement in a better way. Okay, in a better way. Well, doesn't at least mean that one of them has it or both of them have it, right? Are type A. So what I could have done is I could have just said probability. I could do this. I could do probability of at least one type A is equal to 1 minus probability of none type A, sorry. Okay, now remember, this is basically saying the complement of that, right? Because think about this. This would be none. Oops, I keep writing that. The first draw would be none, and the next draw would be none, right? So we have two situations where neither person was type A. Well, everything else besides this one situation had at least one. So by doing 1 minus this, whatever I get will be the leftovers. So 1 minus, now what's the probability of not type A on the first draw? Wouldn't that be 0.6? And what's the probability of not type A on the next draw? Wouldn't that still be 0.6? So this becomes 1 minus 0.36, which is, you guessed it, 0.64. Same answer. You two different ways to do the same problem. This one is actually faster right here, using the fact that it said at least. So a lot of times when they use at least, you can use this little complement to help you through the problem. Okay, so general multiplication rule now. Okay, so now we have to worry about if event A affects the outcome of event B or vice versa. Okay, so conditional dependent probability, this is the hardest part of chapter 4. So it says the probability of B, given that A already has occurred, represents the probability of event B occurring after it is assumed that event A has already occurred. Okay, so it says we read B given A as this notation right here, guys, is what you're just going to have to get used to. This means event B occurring after event A has already occurred. So let's do a thing of blackjack. So suppose you're going to draw 2 cards from a standard deck. And by the way, there's 52 cards in a standard deck, 4 suits, okay, with 13 cards in each. Okay, I might try to send everybody like a PDF of everything that's in a deck of cards. So there's hearts, spades, diamonds, and clubs. Okay, and I forgot to bring one up on here, but I don't want to go searching the internet during my video. But you can bring up like a page on the internet that kind of has them all printed out for you. So suppose you're going to draw cards from a standard deck. What is the probability that the first card is an ace and the second card is a jack? Okay, so this is a way to get blackjack. So it says, what's the probability that the first card is an ace and the second card is a jack, and second card is a jack? Okay, so remember, of every card, there's 4 of each card. So when you reach in and you grab a card out, and let's say what was the chances that it was going to be an ace? So you have the probability of ace right here, right? So I'm doing this, times the probability of a jack, given that you already know an ace occurred, right? Because you're saying you already drew an ace on the first draw. Okay, so now here, how many aces are in a deck? Well, there's 4 aces. How many cards are in the deck? 52, right? So it's 4 out of 52. That's the chance, the probability of that. Now it says the probability of getting a jack, given that you know an ace has already occurred. Well, if you already drew a card and you're holding on to it and it's an ace, how many jacks are left in the deck still? Well, there's still 4 jacks, but how many cards are left in the deck? Think about that. You took one out, so there's only 51 now. This means you have adjusted your probability. This is now a dependent. You are showing that you know how to deal with dependent. I'm just going to do a little cross canceling. This is a 1, this is a 13. And then we end up with 4 over, and let's do 13 times 51. 13 times 51, we get 663. 663. And there is our probability of getting a blackjack in this particular order of an ace and then a jack. Okay. And I'll try to do some more card problems maybe in practice or when we're reviewing for the exam as well. Okay, so now for a tree diagram. So what the tree diagram is an extension of the general multiplication rule, but what it does is it kind of gives you everything, okay? So it says, once again, here's our general multiplication rule. Okay, remember, this is technically, if it were independent, remember the probability of A given B is just probability of A. So if this were independent, we would just replace this with probability of A times probability of B, right? And that would be no different. But because we don't know in general if something is dependent or independent until we've worked with it, this is considered the general multiplication rule. And then you can adjust it to independent if you'd like. Not if you like, if it fits the problem, okay? So it says, given that students attend a final review session, they have a 90% chance of passing the final exam. And given they don't attend the final review session, they have a 15% chance of passing the final exam. The professor estimates that 65% of the students will attend the final review session. Let event A be students that attend the review session, and let event P be students who pass. So what we're going to do is a probability tree or a tree diagram basically gives you like all these outcomes, and it kind of gives you a way to find all of them. Some you don't need, some you're not even going to use, but they're just kind of covering their bases and showing you everything. Okay, so we have the probability of event A. So here it says, let me turn my page real quick. I haven't turned the page in a while. So here it says the probability of passing given that you attended. Right? So what's the probability of passing given that you attended? Well, it says right here, given that a student attended the final review session, that's this, they have a 90% chance of passing the final exam. So this is 0.9, right? Now remember, this P complement right here means not passing, right? If this means passing, this means not passing, okay? So then we say the probability of not passing given that you attended, well, that's the leftovers, that's 10%, right? Everybody okay with this, hopefully? And again, if you guys have questions about the video, you can be sure to meet with me during our meeting times and talk to me about it, or talk to me after class if you're worried that you have a lot of questions. So we have the probability of not passing given that you attended. Okay, now what's the probability of attending and passing? So let's see here. The professor estimates that 65% of the students will attend the final review session. Okay. So the probability of A and P. So we're looking for probability of A and P. Well, that's this right here, right? So probability of attending and passing is equal to the probability of attending times the probability of passing given that you attended, okay? So we know, you know what, let me write that above right here. You know what, maybe I'll do it over here. Probability of attending and passing is equal to the probability of attending times the probability of passing given that you already attended, that you know they attended. Okay, so we know the probability of attending. The professor estimates that 65% of the students will attend. So that's going to be 0.65. Now, what's the probability of passing given that you already attended? Well, you have that right here, right? Probability of passing given that you already attended, well, you know that's 0.9. So this will be 0.9. You know what, I'll do parentheses, that looks better. So let's see what we get. I think it's like 0.585, but let's see. 0.65 times 0.9, 0.585, yep. So we get So we know that one. Now it says probability of A and P not passing. Okay, so let's find that. Probability of A and not passing, complement, and you could use a bar as well, you guys, either one is fine. So this would be probability of attending times the probability of not passing. Okay, probability of not passing given that you attended. Okay, let's see in here if they tell us that anywhere. Well, look right here. It says probability of not passing given that you attended. So we know that this is 0.65 times 0.1. I don't know why I keep using that. 0.65 times 0.1, and that should be 0.065. So you see how the probability tree you get to use this and this to get this, and I get to use this and this to get this. That's kind of the secret to the probability tree, is it has everything built in for you. It kind of goes in with the flow. So now let's see if we can do this one quicker now that we kind of know what's going on. So the probability of passing, given that you did not attend, okay? Well, the probability of passing, so it says right here, and given they don't attend the final review session, they have a 15% chance of passing. So I'm going to go right here and put 0.15. Well, then that means what's the probability of not passing given that you did not attend, right? Not attending, not passing. So that's going to be 0.85, right? That's the complement. That's the leftovers of 0.15. So this is 0.65. This is 0.35. I forgot to put those, right? The probability of attending is 0.65 and the probability of not attending is 0.35. Okay, and I once again, I just got that from up here. He says 65% attend. That means 35% won't. So now, if I want to know the probability of A complement and P, well then shouldn't I just do 0.35 times 0.15? Right? So let's see here. A complement is this, and then A complement, or probability of passing giving that A complement is this. So I'm just going to do 0.35 times 0.15. I'm just trying to show you guys that now we kind of see how the probability tree works. So when we do that, we should get 0.15 times 0.35, 0.15 times 0.35. We get 0.0525. 0.0525. And I could write it out like I did over here, but it's the same thing. Okay. Now here, 0.35 times 0.85, and we should get 0.2975. Okay. So now we have probability of A complement and pass complement. We have attending complement and passing. We have attending and not passing, and we have attending and passing. Okay. So now it says, what percentage of students pass the final exam? Well, what we have to do is we have to find the probability of the students that attended and passed. But are there a few people that may have not attended and still passed? Yes, so I have to count them. Probability of not attending and passed. Well, let's see if we have that. Let's see here. Probability of passing would be this one and this one. So we have 0.585 plus 0.0525. So 0.585 plus 0.0825. Was that what it was? Or was it 525? I think it was 525. I hope that's right. So I get 0.6375. Let's go back here. 0.6375, so 0.6375, but that is actually 63.8% if I round off, right? If I convert this to a percentage, okay? So our answer would be B, 63.8%. So all I did was I found which one of these outcomes had passing. Well, that had passing and that had passing. Notice that this one was not passing and this one was not passing. So those weren't the two outcomes that I was worried about. I was only worried about this one and this one because these have passing, okay? And they wanted to know what's the probability or what percentage of students pass the final exam. according to this tree. So it says, given that students pass the final exam, what is the probability he, she attended the review? This is an example of finding reverse conditional probability by first finding the total probability for the denominator. This is Bayes' rule. So we're not going to go too crazy on this, but this is kind of a nice way to do it. So it says, given a student passed the final exam. So we know, I'm just going to write out the formula, probability, what is the probability he, she attended the review? So probability attended, given that we know they passed. Okay, so that's what we're looking for. So what I'm going to do is I'm going to come all the way up here and I'm just going to write out the general formula. Okay, so probability of attending and passing is equal to the probability of attending times the probability of passing, given that you already know they attended. Okay, so we want it the other way. So what I'm going to do is I'm going to do probability of passing. And again, you could actually mean it the other way as well, but most of the time, the first one is the given. Okay, so you do probability of passing times the probability of attending, given that you know they passed. So here's what we're going to do. What we're going to do is we're going to solve for this. So I'm going to divide both sides by probability of passing. So this will cancel with this, just like in your old school math. So now this becomes probability of passing and attending divided by probability of passing is equal to the probability of A, given that you passed. So this is a slightly harder problem. However, you know all of these things. What's the probability of attending and passing? Well, let's go up here. Probability of attending and passing is 0.585. So what I'm going to do is, let me do some scratch work over here. So I'm going to do probability of passing and attending. Let me take this guy and put him over here. And that will be 0.585 divided by, what's the probability of passing? Well, didn't we just find what percentage of students pass, or the probability of passing? That should be 0.6375. Isn't that what we just found in this step? So I'm going to do 0.6375. And that should equal the probability of attending, given that you already know they passed. So on my calculator, when I enter this in, 0.585 and 0.6375, 0.585 divided by second function answer, which just plugs in the previous one, I get 0.9176. So I'm going to round it to 3. So I'm going to do 0.918. So we get probability of A given passing is equal to 0.918. And that is our answer right there, 0.918. Okay. So once again, a pretty tough concept. Definitely the idea behind this is a little bit harder. The idea of conditional probability seems to be the hardest part for most students in chapter 4. So please come talk to me when you need some help in our meetings. Sampling without replacement, an object or individual selected gets removed and not returned to the population before the next selection is made. Okay, so that's without replacement. But what if it's with replacement? Then it turns it into an independent event. So you take it out and then you put it back. So that makes it independent because you didn't change the probabilities. If you take it out and hold on to it, then that means you're not putting it back. So the probabilities will change for the next event if they are dependent. So tires salvaged from a train wreck are on sale at Get Rich Tire Company. Of the 15 tires offered in the sale, 5 tires have suffered internal damage and the remaining 10 are damage-free. You randomly selected and purchased 2 of these tires, one after the other without replacing. So this is a dependent event because when we draw a tire out, there'll be a different amount of tires from the last time, right? So let's work with this here. So I'm going to kind of just use some abbreviations here. So what is the probability that the tires you purchased are both damage-free? So I'm going to use damage, D equals damaged. And then D complement equals damage-free. Right? Because either they're damaged or they're not damaged. So the complement of damage would be damage-free. Okay? So it says, what is the probability that both tires? So that you get are damage free. So probability of damage free and damage free, right? Let me make some space here. Sorry about that. Okay, so probability of damage free and damage free. All right, well, how many tires have no damage on them? Of the 15 tires offered, 5 tires have suffered internal damage and the remaining 10 are damage free. So I know that this is going to be 10 out of 15 for damage free. Okay, you know what? Let me write this out. Probability of damage free times probability of damage free, given that the first tire was damage free. Okay, so this guy right here will be 10 out of 15. But what is the next probability? Well, think about this. If you reached in and you pulled a damage-free tire out, that means that there is now only 9 damage-free tires. But how many total tires are left in the pile? Well, there's only 14. So this is how we adjusted for the fact that this is a dependent event. So when I do this, let me see. Let's do a decimal for this one. Let's do a decimal for this one. Let's do 3 decimal places. So I'm going to do 10 out of 15. So 10 divided by 15, enter, times 9. Oops, let me do it with parentheses. Times 9 divided by 14, enter. Now, it's 0.42857. If we wanted fractions, let's see if it would give them to us. We could do 3/7. So I'm going to do decimals just for now. So 0.428. We could almost do 0.429. Let's do 0.429. So let's say here, 0.429. This is actually 3/7 or 0.429. That's what we got, right? 3/7? Yeah. So remember, you can use math-frac to put it back into fraction form. So the probability that exactly one of the tires you purchased is damage-free. So that could be exactly one. That could be probability of, well, let's just kind of do a little model for it. So we could have the first draw is damaged and the next draw is damage-free. We could also have the first draw is damage-free and the next draw is damaged, right? Is there any other scenario where only one of the tires is damage-free? No, that's the only 2 scenarios, right? So what we're going to do is we're going to add these 2 situations. So the first one is, what's the probability of damaged? 5 out of 15, right? What's the probability of damage-free? 10 out of 14, right? Because there's only 14 tires left, but there's still 10 damage-free. Plus the other situation, now I'm doing this one. What's the probability of, if we do this new event, damage-free, right? So if we're pretending this is already like, this is a different situation. Now we're finding this other situation that could have happened. Now we're restarting over and setting it up. Damage-free would be 10 out of 15. And what's the probability of the next one being damaged? Well, that would be 5 out of 14. So now if we plug this in our calculator, we get about 0.476. Okay. And that looks like that's about 0.48 if we round off. So we're going to say that's D, 0.48. Okay, so that's how we can do that. All right, let me see. So this is if we were taking the exam in class, these are definitely test questions. I would almost do exactly similar questions, but I think this will be the last problem for this video. And then the next video will start 4.5 and 4.6. Okay, but I think this is plenty to work on. So it says, suppose a fun-sized bag of Skittles has 5 red, 7 green, 6 purple, and 8 yellow. You select 3 Skittles from the bag, one at a time without looking. What is the probability that all of the Skittles are green with replacement? Okay, so now we got to think. The first draw is green, the second draw is green, and the third draw is green, and it's with replacement. So that means it's independent. So that's kind of good for us. We don't have to worry about, adjusting anything. So how many total Skittles are there? There is 26. Yeah, there's 26. So this first one is going to be 7 green out of 26 Skittles. Now we reach in, or we put that Skittle back, and then we reach in and grab out again. What's the chance we get a green? It's still 7 out of 26. What's the chance we get a green again? It's still 7 out of 26, because remember, it's with replacement, meaning you're putting it back in. So then when we do that, we should get decimal-wise about 0.0195. So we'll get 0.0195. Okay, so that should be when we do that. What's the probability that all of the Skittles are green without replacement? So that means green, 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 but this time we're not putting them back. So this will be 7 out of 26 times 6 out of 25 times 5 out of 24. Now, why am I doing that? Well, the first draw was a green, and I'm now eating that one, right? So how many Skittles are left in the bag? Well, there's only 25 now, and only 6 of them are green. So my next draw is only from 6 green Skittles out of the 25. Then after I eat that Skittle, I only have 5 green Skittles left out of the 24. So that means that I have to do this, and this is a dependent event. So that means that we should end up getting 0.0135. Okay. Now, this is also how you could justify that these two events are definitely dependent, because if they were independent events, the given part, given that you know the first draw was a green, means these two would have been the same. But because they're not the same number, that means this is definitely dependent. Okay. So the probability that exactly one of the 3 Skittles is red without replacement. So once again, without replacement means this is dependent, so we have to adjust. So let's go through all the scenarios. Only one of them is red, not 2, not 3, only 1. So we could get a red on our first draw, and then we don't care about red after that. We don't want red anymore, okay? There's another situation that we could get red not on our first draw, but on our second draw, and then not on our third draw, right? Then there's another situation where we could get not red, and then we could get red on our third draw. And these are the only 3 situations where we could get red one time exactly. We don't care what the other color was as long as it wasn't red. So we're just going to do plus and add all these up. And this will be 5 out of 26 are red, right? Let me double check. Yeah. Now, how many are not red? Well, that means there's 21 not reds out of 25, right? Plus 20 not reds out of 24. Now we got to do this other, I'm sorry, times 20 out of 24. Plus the next one would be, what if we did this again and we thought of another situation? We could do not red, red, and not red. So that's this new situation right here, or new event, where that would be not red. So that would be 21 out of 26. Then red, 5 out of 25. Then not red would be 20 out of 24. Now we could do not red, which is this one now, not red, red. So not red, red, right? So when we do all of this, if you guys notice the denominator is 21, 25, 21, 25. 21, 25. Look at the denominator. I'm sorry, that was the numerator. Look at the denominator. 26, 25, 24, 26, 25, 24, 26, 25, 24. Now they're all in different orders, but technically, they're the same fractions 3 times. So what I'm going to do is I'm just going to find one of them, and then I'm going to multiply by 3, and that'll basically account for all of those. So when you do that and you plug this in on your calculator, you should get 0.404. I'll do one. I'll do 5 out of 26. 5 divided by 26, enter, times, what was it? What's the next one we're doing? 21 and 20. Okay. Times parentheses 21 divided by 25 times parentheses 20 divided by 24. Okay. Now, if I want, I could do math and frac. Let me see if it would work. Oops, it didn't do it. So let's do that one. Okay, so this is 0.09423 times 3. I think I did something wrong. Let me do this again. I think I messed it up. Parentheses 5 divided by 26 times 21 divided by 25 times 20 divided by 24. Now I'm going to multiply this by 3 to account for all 3 events. There we go, 0.404. Let's round off to 3 decimal places once again. So this would be 0.404 rounded off. So 0.404. Okay, what is the probability that at least one of the Skittles is purple? Now, I do not want to do the method I just did above to try to figure this out, because at least one purple, that means that I could do, you know, the first one is purple, the second one is purple, and the third one is purple. That counts. I could also do the first one is purple, the second one is purple, and the next one's not purple. That would still be at least one, right? So I'm going to go way back up here, and I'm going to try to use this other technique that I used way up here when I showed you guys this one right here. At least one. I'm going to use this whole, remember I showed you over here, at least one. This is one minus none. So what about if we did one minus the complement, one minus no purples, right? So what I'm going to do is I'm going to do the probability of at least one purple. And that's a whole bunch of scenarios that I don't want to write them all out. So what I'm going to do is I'm going to do one minus the probability of no purple, no purple, no purple. How about that? Okay, so then this will be 1 minus. Now, what's the chance of not getting a purple? So how many non-purples are there? Well, there's 6 purples, so that means there's 20 non-purples. So I'm going to do 20 out of 26 for not purple. Now there's only 19 out of 25. Now there's only 18 out of 24. So when we do this and we hit enter in our calculator, we should get 0.562 if you round off. Okay, so that's the probability of getting no purples. And we use that complement idea of, well, at least one purple. I'm sorry, that's the probability of getting at least one purple. But we used the probability of no purples to help us. Okay, so I think I'm going to stop the video there, guys. Definitely a lot to talk about if you want to meet and during our meetings and ask me questions about this. But thanks for watching, and I'm going to end the video.